Okay, here we've got a collision between two pool balls, each of mass 0.2 kilograms. In the collision, the first pool ball is seen to be moving at 3 meters per second, so I've drawn a top view diagram of the collision itself. After the collision, we know that the second ball, this blue one that I've drawn, which was initially at rest, wasn't moving before, goes off at 1.6 meters per second, and we know that the angle is 60 degrees. They call this an oblique collision. Oblique just means anything but head-on. And the goal is, what's the final velocity of the yellow ball, or the first ball, after the collision? That's what we're trying to figure out. So according to our law of conservation of momentum, momentum before, and there's my before side, has to equal momentum after. I only have the one ball moving before, so I'm just going to label it P1. So the total momentum before is just P1. The total momentum after consists of the final momentum of P1, which I'll call P1 prime, and the final momentum of P2, which I'll call P2 prime. Now it's more convenient to just simply work with the vectors of momentum instead of the vectors of velocity. So P1, when I do a little bit of math, we know it's just mass times velocity. So if I go 0.2 kilograms, because that's the mass of the ball, times 3 meters per second, I will get my initial momentum overall is 0.6 kilogram meters per second. So that's P1. I don't know P1 prime, but I can also get P2 prime. I can calculate it. So similarly, if I go 0.2 times 1.6, mass times velocity, I get P2 to be equal to 0.32 kilogram meters per second. Now P2 will have components, and that's what the goal of this question is. It's going to have an X and a Y component. So I'm going to put those in dotted lines here. The X component of P2 will be to the right, like this, and the Y component of P2 will be up, like that. So this is P2 prime X, and this is P2 prime Y. Now we know this angle right here is 60 degrees. All right, let's start our equations. Now once we have the general equation, our vector equation, the one I've just discovered right at the beginning with conservation of momentum, we can then do the equation twice, once in the X and once in the Y. So let's do the horizontal direction. I'll call it the X direction first. So my equation looks like this. P1X equals P1 prime X plus P2 prime X. Now P1X is the entire thing. The initial momentum is all in the X. So we know this side, 0.6 kilogram meters per second. P1 prime X is what we're looking for. I don't know the value of that. P2 prime X would be 0.32, right? That's the hypotenuse. And I want to get the adjacent side, so I got to go cos 60. So 0.32 cos 60. Now when I work all this out, I end up getting my X component of my final momentum is 0.6 minus 0.32 cos 60. And that gives me 0.44, and I get a positive answer. 0.44 kilogram meters per second. So there's my X component, and it's positive or to the right, because that's what the equation spits out. Now let's do the Y direction. I'll move it up a little bit. So same equation, but now we're focusing on the Y. P1Y initial equals P1Y final plus P2Y final. Now if you look at our picture, there is no Y component initially. So the initial momentum in the Y is just 0. We don't know P1Y prime, but we can easily calculate P2Y prime. And all it is going to be the hypotenuse sine 60. So 0.32 sine 60. In other words, this final momentum that we're looking for has an X component, that we've just figured out to be 0.44 and a y component that we're about to figure out. If there's no y component before, then those two y components have to be equal and opposite of each other after. So clearly I've not drawn it to scale, but that y component and this y component of P2 prime, they have to cancel each other. So I'm going to end up getting P1y prime is negative, when I bring this to the other side, negative 0.32 sine 60, which gives me 0.277. So negative 0.277 kilogram meters per second. So the last step with components, we're almost done, is to simply put them together and get my overall. I can get my angle that way as well. So this is telling me that my final momentum consists of an x component, that's 0.44 to the right. I'm not going to put the units in. And a y component that's down 0.277. So my overall momentum will be this hypotenuse. So that's P1 prime. And when I just simply do Pythagoras, I get my value. P1 prime is the square root of 0.44 squared plus 0.277 squared. And that gives me 0.52. So there's the value of P1 prime, but that's the momentum. Now my direction, I can simply use tan theta. So I'll do that in pink here so we can see the direction. I'll do it down here. Tan theta is opposite 0.277 over adjacent 0.44, and when I solve for theta, of course I've got to do the inverse tan. So when I do that, I get tan inverse of 0.277 divided by 0.44, and that gives me 32 degrees. And you can see that that's below the horizontal, or as stated in the answer, south of east. So we've got our angle. The only thing left is to get the velocity. Well, remember, momentum is mass times velocity, very easy equation. So we know that the momentum is 0.52 kilogram meters per second, and we know the mass is 0.2 kilograms. So when I take 0.52 and divide it by 0.2, I get 2.6 meters per second. And since the velocity is in the same direction as the momentum, we can say it's also 32 degrees south of east.